Hi, this is Cliff Sarin from ComputerWeekly.com, and I'm here today with Axel Neumann at CERN, the home of the Large Hadron Collider. Axel, IT is a big thing at CERN. The numbers are astronomical. Can you give me some figures?
Yeah, we collect lots of data. We have, so the experiments that we have, there are 4 with the Large Hadron Collider. They are looking for very rare things. So to find them, they need to collect lots of them. And that translates to a few, I believe 4 petabytes per year for all the experiments.
And specifically, what are you involved in?
The experiments have their own analysis software, but of course they don't want to reinvent the wheel, each of them. So CERN decided to provide a few basic ingredients, and I'm working with one of the basic ingredients. It's called Root. It's a project which does the data storage of C++ objects, actually. All software over here is C++. Then the physicists load this data again, and they analyze it. So we have mathematical, statistical tools, and we go all the way up to the final publication, so we generate the PDF plots for them.
How many people use your code?
That will be basically as many as CERN has users, which is 10,000 all over the world. Within Europe, of course, the member states of CERN, but also the US is a large contributor. And Asia, we have India and Japan and China, so it's really the whole world which uses it.
And Root is quite a sophisticated project. There's lots of code.
Yeah, it has some tricky ingredients. It's 2.5 million lines of code.
2.5 million?
Yeah, and we are 6 developers here at CERN. So yeah, it's a challenge.
Well, that's amazing, because Windows has, what, 25 million and is used by 100 million or so people.
Yes.
That's fantastic. I mean, how do you keep the code secure and high quality? How do you achieve that?
Of course, we have our first level check, which is our continuous integration test. We build Root continuously on several platforms, Linux, macOS, Windows, with all the different compilers, Solaris, not to forget. Because we want to get feedback from the compilers, they see issues very early. We also have unit tests and an integration test suite where we check more complete feature sets. And then in the end, once the experiments decide they want to go to the next Root version, they take it and run their physics analyses, a few test cases with this new Root version to make sure that they don't get differences in physics.
I guess having a bug in Root is a pretty bad thing.
Yeah, it spreads. Usually it gets noticed quite quickly and then we need to repair it. So of course we want to repair it before it shows up. And one of the problems we of course always had with generating tests is that we don't really know what to test, right? Or there are certain cases which we simply cannot test. Root is used on the grid, which is a worldwide sort of batch system. And the processes run for many, many hours there. And so once in a while, you have a crash because some connection got dropped or whatever, and then people report us that crash and ask us to fix it. But I mean, how are we going to reproduce that, right? There's no way for us to have exactly the same state, to come up with the same state, reproduce the same state. And so one obvious approach was to not only look at tests and dynamic analysis tools like Valgrind, which we also heavily use, but to use static analysis tools, which look at the code irrespective of what is actually executed.
And static is, so this is before it's rolled out?
So we use dynamic analysis tools like Valgrind, but we found that static tools give us a new dimension, basically, of testing. And after checking out a few of the tools which are very noisy and difficult to work with, we found Coverity, which is really very satisfying in the quality of its reports. So that's now being used by Root. We worked on all the 4,500 reports that we got from Coverity. We're now at 0, very proud of it. And by the experiments on a code base, in total, I guess, of about 50 million lines of code.
Axel, it's amusing almost that you describe software development as noisy. What do you mean by noisy?
Well, the reports can be noisy of static analysis tools because they are often basically brainless. They see a certain software construct and they say, this could, in certain occasions, in certain contexts, provoke an error. Okay, but then the developer says that is not actually the context that it's used at, so ignore. Once you've done that hundreds of times, you don't care about these reports anymore. They're not, you cannot take them serious anymore. Whereas with covariety, much of that filtering is done automatically, so you really only see the relevant reports. We have, for root, we had a false positive rate of 11%, which is amazing for a static analysis tool.
And 11% of 2.5 million lines of code. That's very good, is it?
Well, 11% on 4,500 reports. So yeah, you know, that's divided by 6, but still keeps the motivation high, yes.
Excellent. Axel, thank you very much.